not going to make my kids do anything. Oh, that's my, that's not yours. Oh, that's worse. No, it's not your bro.
Gotta get that three-man lead going.
Okay. Moving on with chapter 4 today. Next week, just looking ahead, we have one more. We're going to cover the first 4 sections. And then we'll have a quiz review and then a quiz on Wednesday next week. And then we'll finish up the rest of chapter 4. So we will get the chapter 4 test done in before spring break. Because I think we have, we got 5 days next week. Next week's already March. And then the week after that is, I believe, the last week before spring break. So that'll get us in through chapter 4.
How many more chapter tests do we have left?
3 more. We've got 6 total.
Including this one or not?
Well, we just got done with chapter 3 tests, so we're on chapter 4 right now. So yeah, we're halfway done basically. All right. So the good news that you guys may or may not be excited about, that'll make this fun, is we aren't going to do long division today. You guys remember long division?
Yeah.
Okay. We're not going to do long division. Not kind of a tedious process.
Good.
Okay. I'm only going to, just because there's very few times in college algebra, especially where we have to do long division, and so we're only going to do synthetic division.
I think you said you wanted to. I never said that.
Yeah. Well, guess what? I'm here after school today, so come in and me and you can have a good session of long division
I
together.
despise long division.
Put in that extra work.
Don't you want to be a teacher? That English.
I thought you were being
What happens if one of your students comes in and asks for help with their long division?
Then I'm going to tell them like the subtouch. Wait, I'm not failing in class, so I can't. I suck at math. I hate math. You're basic. Just kidding, I don't hate math. That much. You're basic. I have a C. Oh, wait, no, I'm a B.
Just don't be that teacher that someday says, math, you guys are never going to use your math, you know.
No, yeah,
Because
I'll probably use
I've heard of it, teachers that'll say that, math, I don't use any of the math that I've had,
Here?
Huh? Maybe not.
I'm never going to use
You can name drop, it's okay.
No, I would never do that.
it. Was him.
You can blink in Morse code.
It was probably back. No, Dexter doesn't know.
So there's a lot of different ways that division can be written, okay? And this one would be like a polynomial on top divided by a polynomial on bottom. Sometimes they may be written like side by side where we'll take this polynomial divided by this polynomial, but we always got to take the higher degree divided by the lower degree. And usually, if we had one that was higher than a degree of 1, we would have to do long division, so that tells us that synthetic division is all going to be linear, and we're only going to see dividing by a degree of 1. And so when we write this out, just kind of remember the process of synthetic division, because it's been a little bit. We always start with this box, and in that box, it would be kind of like setting x plus 1 equal to 0, whatever's on bottom, and that gives me -1. So -1 is going to be the number that goes in the box, okay? I know a lot of people just say, well, it's always the opposite of this, and that is true too. But sometimes it's written as a factor, okay? What we're going to see later on in the lesson today is sometimes it'll say, let's check this 0, or let's check this to see if it's a 0. In this case, it's written as a factor. X plus 1, as we've seen the last couple of days, is what we call a factor, right? X plus 1, x minus 2, those are the factors of the polynomial. Then next to the box, we're going to put our coefficient. So if there's no number in front, we're going to assume it's a 1, 2, -5, -6. We're going to bring down the 1. And from here, it's just being able to multiply and add. We're always going to take the number in the box times the number down below. So -1 times 1 would be -1. And then we add straight down. 2 plus -1 would be 1. And then we just keep repeating that same process over and over. Negative 1 times 1 would be negative 1. Negative 5 plus negative 1 would be negative 6. Negative 1 times negative 6 is 6. And this gives me, I always draw a line in here, and this last number here is always our remainder. Okay, if I get a remainder that's equal to 0, that means that negative 1 is a 0 of this polynomial. It's one of my solutions, right? And drawing that back to the last couple of days, if we were to graph it, because we're going to do a lot of graphing and we want to kind of tie all this together, this would be, if I were to graph this polynomial, negative 1 is one of the places that it will cross the x-axis. Okay, it's one of the zeros of this. If I have a degree of 3, how many times could it cross the x-axis? 3, right? Eventually, we're going to find all 3. Right now, we're just checking to see if it is a 0. And sometimes it won't even ask you that question. It'll just say, go through synthetic division, and then just tell me what my solution would be. So it doesn't always have to have a remainder of 0. Okay, so that's my fault. I was talking about the remainder. If I wanted to write the answer of this problem, we're going to start, we started with a cubic. I want to write this answer as a polynomial, okay? So I'm going to drop it down by a degree. I started with 3. This is now going to be 2. So this would be 1x squared plus x minus 6 with the remainder of 0. Hey, and so if they ask you to write your answer as a polynomial, that's what it's going to look like. We just start filling in with x's, but it's always going to be 1 degree less than our original. Look at one. This one's a little bit different. And like I said, these could be written side by side. Here's another way you might see some of these problems written. It really doesn't matter. I mean, if you write it as like with a fraction bar, if you write it side by side with the division sign in between, it all means the same thing. We're just doing division. Okay, what would go in our box? Negative 3. So x plus 3 equal to 0. Okay, now here's the one thing that we want to pay attention to. And I didn't talk about this on the last one because everything was good. And really on the last one, I didn't even finish this. So if we do that here, the one thing that's going to be different about this problem is as I write this out, number one, make sure it's in standard form. So here we're starting with 4. 4 is definitely our highest exponent. And as we work our way down, what we're going to notice here is we need to make sure that every exponent is accounted for. So we start with 4, 3, but it's missing a 2, right? It doesn't have an x squared in here. So when we write these coefficients out, we're going to start with 2, and then 7, and it's missing an x squared. So we have to put a placeholder in for x squared. Okay, that's the part that a lot of times gets forgotten. If you don't put a 0 in there, you will get a different answer, and it'll be the wrong answer. So we got to make sure we pay attention to that. And then we got a 1, and we got a negative 12. And then once we have it set up, then the synthetic division is the same. Bring down the 2. And then it's just multiply and add from there. Okay, and this is always my remainder. And like I said, you won't always get a remainder of 0. A remainder of 0 is what we want to be, especially if we're trying to decide if it's a 0, okay? But sometimes it's just going to ask us, what's the quotient? What's the answer to the division problem, right? Quotient is the answer. And so the quotient here, we're going to write it as a polynomial. We started with a degree of 4, so we're going to drop it down by 1. So this is going to go 2x cubed plus 1x, and I could just put an x there. I don't have to put a 1 on it. Minus, x squared, minus 3x plus 10 with a remainder of negative 42. And that would be our answer. How can you? And what that means is that this is not one of my zeros. Okay, so if I get, and we'll talk about this more in just a second, but if I looked at this graph right here and wanted to see does it cross the x-axis at negative 3, then we would say no, it doesn't. Okay, and so if it's a zero, if it's one of the zeros of that polynomial, it will get a remainder of 0. Okay, but it won't always be a remainder of 0. We could get all kinds of different remainders. Okay, but 0 is what we want to happen because we want it to be a factor. But there are going to be some questions today to say, is this a 0 or is it not a 0? And so that remainder of 0 is what we're looking for. And I think it'll make more sense. I think your question will make more sense here in just a second too. Because we have this theorem called the remainder theorem. And this ties to some things that we did earlier in the chapter. If I give you a polynomial, we had some problems like this earlier in the chapter, and we did it a little bit different way. And what I'm going to tell you from here on out, I don't necessarily care which way you're going to do. I'm going to show you several different ways that you could kind of approach this kind of problem. But it's going to ask me to check multiple numbers. I want to plug 1, -2, and 3 into this. And when we did it earlier in the week, we took 1, we plugged it in for x, and we found out what we got, right? We evaluated the function. And we kind of cheated a little bit when we did it early in the week because since we're doing multiple of these, I told you guys the quick and easy way to do it would be put this into your calculator, right? Go to your table of values and say, okay, when x is 1, what's my y value going to be? When x is -2, and when x is 3, what do I get, right? And so it was kind of a little bit of cheating because we didn't necessarily have to plug it in, okay? And it just saves time more than anything else. And so that's what we did earlier in the week, and we could definitely do that here, okay? But the remainder theorem uses synthetic division. And so when I do synthetic division here, this is not a factor. This is just a number that we want to check, okay? Not necessarily a 0. If I get a remainder of 0, then it'll be a 0, okay? And that's where the remainder theorem comes in. So we're going to put 1 into synthetic division. Our coefficients are 1, -6, 11, -6. And we're going to go through. So when I plug in 1, I get 0. And so here we would say, yes, this is a 0 of the function. If I plug in -2, so we're going to essentially do this 3 times, okay? Now I'm going to do it all over again, and I'm going to plug in -2 this time. 1, -6, 11, -6. And this one, we would say no. We get a remainder that's not 0. Any number other than 0 is not a 0. So we get -60. So this one is not a zero of the function. My answer is a simple yes or no. And that's why we can get a remainder other than zero, and it doesn't really help us. Okay, it's not really a zero. And then the last one we're going to try is 3. And we get a remainder of 0 again. Okay, so this one we would say yes. Because it equals 0, then it would be a 0. Okay? Now, I just want you to understand and see the link here, okay? And understand what's happening. If we were to graph this, right, and this is really kind of what we did, or if you just put this into your calculator, this is kind of what we did earlier in the chapter, is I can take this function, okay, this one's going to be very similar, but we're going to take it a step further. Instead of just plugging in good old nice integer numbers, is an I a zero of a function? Well, when I have, just think about last chapter, right? When I graphed a quadratic, if the parabola did not cross the x-axis, we had imaginary solutions, right? And we talked about how we could find those imaginary solutions. We could do the quadratic formula, and we could get there. In this case, we're not finding them. Eventually, we will find the imaginary solutions. Today, it's more of just checking to see, are these actually solutions of this polynomial? Your calculator really wouldn't help you here a whole lot because we can't find imaginary solutions off of our calculator. So here we got to check it. Okay, and we'll talk more later on throughout the chapter about how we'll get there and how we'll find those on our own without them being given to us and just simply checking it. But for right now, we're just checking it. Okay, now, don't treat I any different than any other number. I'm going to put I into my box. We're going to put our coefficients. All our coefficients, all our exponents are accounted for. Okay, and this looks like it's going to be kind of difficult, and it'll be a little bit different, right? But if I take I times 1, that just gives me I. And then I add straight down. So that would be 2 plus I. And then if I take this I and multiply it by these two things, we're going to distribute here. Okay, this is not in parentheses, but if it helps you to put it in parentheses, then maybe we should put it in parentheses. Okay, I times 2 would be 2I. I times I is I squared. But what is I squared really? Negative 1. So this becomes negative 1. We would typically put it in front. You're right. So I could rewrite that, or I could just say these are going to cancel, right? 1 and negative 1 are going to disappear. And when I add the top to the bottom, all that leaves me with is 2I. And then when I take I times 2I, I get 2I squared. But I squared, once again, is really negative 1. So that's really 2 times negative 1, which is really negative 2. And 2 plus negative 2 is 0. So is it a 0? Yeah. Because we get 0, then it's a 0. Okay, and I'll show you an easier one here in just a second, but if this is 0 right here, we can use either this or I can go back to the beginning. And I know that you might look at this and say, oh, this will be easier because these are nice whole numbers, right? But I can also put negative I in with these coefficients. And so if I moved it down, maybe that would make a little bit cleaner. I can put negative I in here, and I can use 1, I can use 2 plus I, and I can use 2I. I'm just going to bring those down with it. And this time I want to try negative I with this. And I'll show you why this is a little bit easier than using those nice whole numbers. When I bring 1 down, negative I times 1 is negative I. And if I add these together, the i's are going to cancel, right? And that leaves me 2. And then negative I times 2 is negative 2I. And that gives me a remainder of 0. Okay, here's what happens also, and we're going to see more examples of this as we go throughout the chapter, but I started with cubic. This would be quadratic, but do we really want to write this equation as a quadratic equation? No, that'd be ugly, we would never do that, okay? But this is a linear equation now left. So we went from cubic to quadratic to linear. Every time we break it down, as long as we get a remainder of 0, we keep dropping it down by a degree. So this equation here is really x plus 2. And if I set x plus 2 equal to 0, I get x equals negative 2. And that is also a 0. So all 3 of those would be yes. The reason why your calculator does not help here, and you could put this into the calculator if you want to, but if I graph this one, it's going to look something like this. And it may not be perfect, but it's a cubic function. It crosses the x-axis at negative 2, because negative 2 is a 0, right? The other 2 solutions are imaginary. Okay, and we wouldn't be able to find these 2 imaginaries from our graph. Here we verified that they were zeros by using synthetic division, but only because we got a remainder of 0. That's
Why would they be on the graph?
do what?
Like, the imaginary solutions, where would they hit?
They don't,
Because they're imaginary.
because they're imaginary.
So imagine it hitting.
But like, yeah, I know,
Because
if
it's
I'm
not-
imagining it hitting where it has to hit someone, where would that be?
No, that's only if it's a real solution.
That is your imaginary.
Real solutions will hit on the graph. Imaginary solutions will not. Think about last chapter.
Imaginary solutions are like, if the graph was like 3-dimensional, right?
Right. Yeah. Well, yes. Like we would have like a different coordinate plane, and like that would get into like some trig and stuff like that. Yes. And so it would not be on the 2-dimensional plane, which is kind of what she's
So it
talking
would hit
about.
somewhere.
Not on your typical XY coordinate plane.
No, Hudson, it doesn't hit.
Not
The
on
coordinate,
the sequence.
the coordinate plane that we know of as of right now, no, it would not hit. And that kind of goes back to last chapter, right? We said this did not have any real zeros. What are the imaginary zeros? And we could find the imaginary zeros, we just can't find them off the graph, because they don't necessarily hit anywhere special on this XY coordinate plane. And I get what your question is. I'm not saying your question was dumb, because it's a great question.
No, you can say it's dumb.
I mean, but I just don't want you to, I'm not trying to like say, oh, you know, what are you asking that for? But because we keep talking about, oh, well, it's gonna hit the x-axis, so that's a 0, right? But if it doesn't hit the x-axis, that means it's not a real 0, it's an imaginary 0, but we wouldn't be able to just look at the graph and say, oh, hey, there's my imaginary 0.
But it's still changes.
And that's why I keep going back to the fact that when we have a graph that doesn't cross the x-axis, there are zeros, okay? Because even last chapter, I had a few people say, Oh, no real solution. Well, that's true. That's right. But we don't get to say no real solution anymore. Now we get to find those imaginary solutions. And we'll have other ways to find it. We won't get into that quite yet today. Today is just, is it a zero or is it not a zero? But next week we'll get into how we can use synthetic division, and we can use all these things together to find out what that solution is. Fun times, right?
You get it?
Mind's blowing,
You
right?
just gotta pretend like
You
they're
just
not
gotta imagine the moment.
there. Imagine they're not there.
You build a program that gets it to draw a graph that shows up on your calculator to show where those imaginary zeros, you can make a lot of money.
That's the solution, yes.
Because that's what everybody wants, right? I want something that's going to show me what these solutions are going to be.
What's math has to do?
Okay, I'm going to show you this real quick. Only because the wording of questions like this can be a little bit confusing sometimes. We saw problems like this the last couple of days in a couple different instances. Yesterday when we graphed it, we talked about finding the zeros, and we talked about finding the zeros using factoring. So this says to factor and solve. And so when I had 4 terms, what was the factoring method that we used to factor this? Grouping. Okay? So if I try to do grouping here, and that's really the only method that we know of right now to factor a 4-term polynomial like this. So if I were to write this out and try to group it, we'll do our 2 groups of 2. Out of the first group, I can take out an x squared. Out of the second group, they don't have anything in common, so that would just be a 1. The 2 parentheses must be the same. And they're not, okay? So we can't truly do this one by grouping. Grouping doesn't work here. Only works if these 2 parentheses are the same. So I'm going to show you a really quick shortcut here. Okay, and you could probably do this on a lot, only if we have integer solutions, only if our answers do cross the x-axis. If it was imaginary, we wouldn't be able to do this method. So what we're going to do is we're going to kind of go backwards. We're going to solve it first, and then we're going to use our zeros to see what the factors are. Okay, our factors are always written as parentheses. Okay, and so we're going to do both here. Where does it cross the x-axis? Use those zeros to find our factors. Okay, so let's graph this one real quick. X cubed plus 4x squared plus x minus 6. Completely from our graph. Those are our solutions, our zeros, our x-intercepts. You can call them a lot of different things. What would be the factor that would match up with negative 3? X plus 3. Good. And then negative 2 would be x plus 2, and then the last one would be x minus 1. So that's kind of our cheating method. We can solve it first. We can use our zeros to find our factors. These are the 3 things. If I multiplied these 3 things together, they would get me back to here. Okay? And that's how we can come up with that polynomial if we had to. Okay? But you're going to have some questions that ask you to factor and solve. And so a lot of people want to do it in that order. But if it doesn't factor by grouping, then we kind of have to work backwards. There's really no other way to get those factors other than this, as of right now at least. Okay, I'm going to show you this last example here. And this one's a little bit easier, doesn't have any imaginaries, and we're really not going to see any problems today where we're going to actually find imaginary solutions. That'll be next week. Something to look forward to, right? Today, we'll check to see if imaginary zeros will work, but we won't actually find them on our own. The problems that you're going to see today are going to look more like this. F of x cubed minus 3x squared minus 6x plus 8. Okay. And there's a couple of different ways that we can go about this, but I'm going to show you kind of the shortcut. If I tell you that x equals 1 is a 0 of this function. And sometimes we have to, we may be given that sometimes, and sometimes we may have to find that from our graph. And to find that from our graph, we would graph it, we would look at our graph, and we'd say, yep, it crosses the x-axis at 1. And if you graphed this one, it would indeed cross the x-axis at 1, okay? And that's how you could verify it. But I'm telling you right now, this one has 1 as a 0. So we don't have to verify it. Unless you don't trust me. Okay, so we're going to put 1 in here. And we're going to put our coefficients. Go through synthetic division. Okay. If I tell you that 1 is a 0, we have to get 0 as a remainder. If I don't get 0 as a remainder here, then I have done something wrong, okay? I have to get 0 as a remainder, which I definitely do, okay? So that's good news. Now, what we could do here is we could do a lot of different things. Remember that this leftover equation is this. X squared minus 2x minus 8. Because we started with a cubic, we drop it down by a degree. This is our leftover equation. And if I ask you to do the same thing we did on the last problem, factor and solve in whatever order you want to do it in. We already know one of our solutions is 1. We already know that one of the factors is x minus 1. We have a quadratic equation left over here. Can I factor this quadratic equation? What would be the method that I would use to factor this?
Not Dobbs, but is it Dobbs?
Not Dobbs.
It's-
Dobbs would have to be just, not sums. Product and sum. Yep.
Yeah.
What multiplies to get negative 8 and adds to get negative 2? Okay. We just got to watch our signs, okay? Negative 4 times 2 would get negative 8. Negative 4 plus 2 would add to be negative 2, okay? So those are our 3 factors. Our 3 zeros, we already got 1. Then we would have positive 4, and we would have negative 2. So those are my 3 factors, and those are my 3 zeros. So that's where synthetic division is going to come into play. If I get a remainder of 0, I can drop it down by a degree, and then I can do anything I want once I have a quadratic, right? I could try to factor it. We could do quadratic formula if we want to, right? But probably not. If we can do another method, we probably wouldn't do that. I mean, heck, you could even graph it. And if I graphed this right here, this polynomial is going to cross the x-axis at these 3 values. If I graph this quadratic, it's going to cross the x-axis at those 2 values, right? So do they tie together? Absolutely, right? We're trying to find the zeros of the original polynomial. But as we break it down, we can use that to find other ones as well. So if it says to factor and solve, we want to write both answers out. These are the factors that would get me back to here. These are the solutions of the polynomial. Okay, questions on that? And this is how most of the answers, I think maybe even all the answers that you're going to get today are going to be nice integer numbers, positives or negatives. Next week we'll get into some that aren't quite that straightforward. All right, so assignment for today. Okay, the very first problem, number 10, it says to use long division, but I didn't show you long division unless you're Ryler and you have a burning desire to do long division, and then you can go for it.
No.
No? Oh. Even if I gave you extra credit points? So number 10. Number 10, you can use synthetic division. The other one, number 30, it says evaluate f of 2 plus 3i. I'm not going to make you do that. Okay, that one gets pretty nasty because it's a lot of foiling with i's and wouldn't be a whole lot of fun. Trust me. So the only ones that I'm going to ask you to check by doing synthetic division would just be if it was like 3i all by itself, the math is a little bit easier. But when it gets to be 2 plus 3i and it has like 2 terms in it, that becomes a little bit tougher to do. Not impossible, but just gets a little bit